Perfect. So let us review different tests when we start analyzing series. First of all, just one important series for you, harmonic series. We define harmonic series this way. We say that we have a series 1 over n starts from 1, goes to infinity, and this is called harmonic series. So the terms of this series are written this way: 1 plus a half plus a third plus the rest of the terms. Remember that when we introduce sequences, if you have just a sequence like 1 over n, so I'm taking the general term of my series as a sequence that we define in 11.1. We take the limit, 1n goes to infinity. This is 1 over infinity, which is equal to 0. You might say, hey, this sequence 1 over n is convergent. Well, of course, it's convergent. You take the limit and it's going to 0. But when it comes to a series of that sequence 1 over n, by adding the terms, we define a series. This series is not convergent. If we add all of these numbers together, it's getting larger and larger. It's going to infinity. So as a series, it is a divergent series. As a sequence for the general term 1 over n, it's a convergent sequence. So there is a difference between series and sequence. You always have to be careful when you're analyzing a sequence or a series. Very well. One theorem for you. This theorem says if you're sure a series is convergent, if sigma an, n starts from 1 to infinity, is convergent, then for sure you can say that the limit of the general term is 0. Then the limit of an while n goes to infinity for sure is equal to 0. Guys, note that if you have this condition in the convergent series, it results in the limit of the general term be equal to 0. It's not equivalent. Be careful about that. It's not saying that the series is convergent if and only if the limit of the general term is equal to 0. It is wrong. The contrapositive of this theorem says if the limit of the general term while n goes to infinity is not 0 or doesn't exist, contrapositive. The negation of conclusion, then the negation of your hypothesis. Then you can conclude that then the series is not convergent, it is divergent. So if the limit of the general term is not equal to 0 or it doesn't exist, then you can for sure say that, hey, this series is divergent. Remember that these are not equivalent to each other. What's the meaning of that? Consider the harmonic series. For the harmonic series, 1 over n starts from 1, goes to infinity. The limit of the general term is equal to 0, but the series is a divergent series. So they are not equivalent. If then. So what is our goal? Our goal is to be able to analyze a series. We have nice tests to help us analyze the series. So we're going to go over all of the possible tests for a series. Then we're going to go over some examples. Integral test. Integral test to analyze a series. Well, this test says if f is, it has three conditions. If f is continuous, positive, and 3, decreasing. What's the meaning of decreasing? It means that if you take the derivative is less than 0 on an interval, 1 to positive infinity. Then, if the series is defined as the series of n starts from 1 to infinity, and an is equal to f of n, we have the following test. If the integral 1 to infinity of f of x dx is convergent, then our series is convergent. Then our series is convergent. And if the integral is divergent, we have a divergent series. Divergent, then our series is divergent. This is called integral test. So continuous, positive, decreasing, it means that the derivative is less than 0. So let's write down this test here. Our very first test is integral test. The next one is called P-series. P-series. A P-series is defined this way. The sum 1 over n to the p, n starts from 1 to infinity. If you have a P-series, it means that the exponent is p. I'm not talking about the base. The exponent is p. We have this case. If p is greater than 1, then we have a convergent series. If p is less than equals to 1, we have divergent series. If p is equal to 1, you actually have the harmonic series. If p is equal to 1, then we have harmonic series, which we all know is a divergent series. So if you can have a P-series, it helps us to analyze convergence and divergence of our series. N starts from 1 to infinity, and P is the exponent. Perfect. Next test, comparison test. Comparison test says, suppose you have two series with positive terms. Let an and bn and starts from 1 to infinity and starts from 1 to infinity are two series with positive terms. And suppose you have this condition. The general term of the first series is less than or equals to the general term of the second series. Then here you have two conditions. If sigma bn is convergent, so as sigma a. If the larger series is convergent series, for sure you can say that the smaller series is convergent. If the smaller series is divergent, then the larger series is divergent as well. N starts from 1 to infinity is divergent, so as series Bn and starts from 1 to infinity. So we can compare two series if their terms are positive and the general term of the one of the series is less than or equals to the general term of the other series. If the larger series is convergent, it means that the smaller series is also convergent. Remember that we define partial sums. If the limit of the partial sums of the larger series exists, then the limit of the partial sums of the smaller series for sure exists. It doesn't make sense this guy goes to a fixed number, unique number, and this guy goes to infinity. Then you get infinity less than a fixed number. It doesn't make sense. So we have comparison test, and we also have something that we call limit comparison. It involves, again, two series with positive terms. So let an and bn be two series with positive terms. Then you take the limit of the ratio an divided by bn. N goes to infinity. And this is equal to a finite number like c, which is positive as well. Finite number like c, which is positive. I'm not talking about infinity. It must be a nice finite number. Then an and bn, these two series, are both convergent or both of them are divergent. Are both convergent or both divergent. So if an is convergent, bn is also convergent. It's a series, and if the series bn is divergent, for example, the series an is divergent as well. Okay, so let us list them all here. P series, comparison test, limit comparison, so here you have comparison test. then limit comparison. Okay. Now we're going to talk about alternating series. Definition of alternating series. So an alternating series defined this way: the sum -1 to n minus 1 bn, and starts from 1 to infinity. And we have these two conditions for our bn. Bn is decreasing, and then you take the limit of bn while n goes to infinity. This is equal to 0. So if you have an alternating series with these two conditions, then this series is a convergent series. Very well. So alternating series. So when you see a series, you need to check the integral test. If the conditions are met, or if the conditions are not met, you have to move on to the other tests. If it's a p-series, can I use comparison test? What if I use a limit comparison test? How about alternating series? Is it similar to a format of alternating series? If the limit goes to 0, then we have a convergent series. Then we have absolutely convergent series. So we have a definition. Of absolutely convergent series. So suppose you have a series, any series. Let sigma an, and starts from 1 to infinity, be a series. If the series of absolute value of the terms, it means that we're just focusing on positive terms. If the series of absolute value of an is convergent, then we say that our original series is convergent, it's absolutely convergent. That's sigma an, and from 1 to infinity is absolutely convergent. It turns out that we have a theorem. If a series is absolutely convergent, then that series is convergent. If a series is absolutely convergent, then it is convergent. So alternating series and absolutely convergent. Very well. Ratio test and root test. Ratio test and root test. So suppose you have a series. And so let's sigma an, and starts from 1 to infinity is a series. Very well. So ratio test says take the limit of absolute value of an plus 1 divided by an while n goes to infinity. If this limit is equal to a number like L, you have three conditions. If L is less than 1, then you can say that, hey, this series is absolutely convergent. Absolutely convergent. If this is greater than 1, it is divergent. L is greater than 1, it is divergent. If L is equal to 1, this test doesn't work. The test does not work. This is called the ratio test. We form the ratio, absolute value of the ratio an plus 1 divided by an. Root test. Root test says, okay, instead of forming the ratio, find the limit of the root, the nth root of absolute value of an while n goes to infinity. The same here. If this limit is equal to L, you have these three conditions. If L is less than 1, the series is absolutely convergent. If it's greater than 1, it is divergent. And if L is equal to 1, then the root test doesn't work. So, ratio test and the root test. Okay, let's take a look at some of the examples here. So these are the tests. You need to know all of them. Some examples. Analyze the following series. So the first one is the sum ln of n divided by n starts from 1, goes to infinity. The second one is the sum 5 divided by 2n squared plus 4n plus 3 and starts from 1 to infinity. And C, let us work with alternating series, -1 to the n. And here we have 3n divided by 4n minus 1 and starts from 1 to infinity. Okay, perfect. So here we go. Let us start. I have these series. I'm just going to start working with the series ln of n divided by n. Which test is the best here? Which one gives me the result? So I'm looking at ln of n divided by n. I already know that from elementary calculus that ln of n divided by n is decreasing. So ln of n divided by n is decreasing. Okay, of course, it's a decreasing function. Is it positive? If you find that the terms of these, while n is 1, while n is 2, while n is 3, and so on, it's going to be positive. Also, it is continuous. Also continuous. So it seems like it satisfies the integral test. So let us apply integral test. Okay, perfect. Integral test says if I take the integral of f of x dx and it is convergent, it means that my series is convergent. So ln of x divided by x dx. You can apply u substitution. U is ln of x. So u is ln of x and du is 1 over x dx. I have everything that I need here. So by applying u substitution, I get a half u squared, which is ln of x to the power 2. X starts from 1 and stops at infinity. So if I plug in infinity, it gives me infinity. So what's the meaning of that? It means that the integral divergent. You have a divergent integral. It means that your series is a divergent series. For the second series, 5 divided by 2n squared plus 4n plus 3. Can I apply integral test? Okay, if I want to take the integral of this quantity on the denominator, how do I find that integral? It makes it complicated. So what if p series? It's not exactly the same as 1 over n to the p. It has some terms here, but if I can compare it with a p series, it makes it much more easier to analyze this series. Okay, so your an is equal to 5 divided by 2n squared plus 4n plus 3, which is less than equal to bn, which is 5 divided by 2n squared. Okay, I have 5 divided by 2 times 1 over n squared, and the series 1 over n squared is a p series. We have p series 1 over n squared. And if you rewrite this series, you get 5 over 2 times the series. That coefficient doesn't change the series. So in this case, p is equal to 2 greater than 1. So your p series is convergent. So comparison test says since the larger series is convergent, the smaller series is convergent. By comparison test, this is convergent. Okay, perfect. What about this guy here? Integral test. Well, integral test says I have to have positive terms. Because of -1 raised to n, I don't get positive terms. What about p series? No, it's not like a p series. I need to have 1 over n to the p. And even if I want to compare it with a p series, what p series works the best here? Limit comparison, again, I need to have a series to compare it with. What about alternating series? Well, it's very similar to an alternating series. This is similar to the sum -1 to the n minus 1 dx. Okay, so this is an alternating series. If it satisfies those two conditions, then we can say that, hey, our series is convergent. But let's check. First, bn is decreasing. So let's separate these. And the second condition was the limit of bn while n goes to infinity must be equal to 0. Okay, what is the limit of my bn? The limit of bn is 3n divided by 4n minus 1, while n goes to infinity, which is 3/4, which is not equal to 0. So I cannot use the conditions that I mentioned in alternating series and conclude that it's convergent or divergent. So what if we want to know if it's convergent or divergent? Alternating series test doesn't work here because this is not 0. So alternating test, series test doesn't work here. So is it convergent? Is it divergent? What should I do here? Which test works the best? Can I use ratio test, root test? What if I use ratio test? Ratio test says find the limit of absolute value. It means that I can get rid of -1 to the power n. I get 3n plus 1 divided by 4n plus 1 minus 1 divided by 3n over 4n minus 1. Now I need to find this limit while n goes to infinity. If we simplify this, you get the limit of absolute value. If I distribute this and start taking the limit, here you have 3n plus 3 times 4n minus 1 divided by, here you have 3n times 4n plus 4 minus 3, 4n plus 3, while n goes to infinity. So what is this limit saying? What do we have here? Here you have 3n times 4n, you get 12n squared, and here you have 12n squared. So what does it give us? This is equal to 1. It means that we cannot use the ratio test. Doesn't work. What if I use the root test? How about the root test? The root test says you have the limit of nth root of -1 to the power n, and here you have 3n divided by 4n minus 1. What about this test? And here I have absolute value, so I'm not worried about -1. Can I use this test? Does it work? Think about this question.